Alright, so we know that we have certain mixtures of different solutions that can create a precipitant, that can create something that will drop out of solution as a solid. Now let's work out how we determine what those are and how to write the correct chemical equation for those reactions. So we have a four-step process here we're going to use to write out these chemical reactions. The first one is to determine what ions each aqueous reactant has. Now sometimes this is done for us. Sometimes we're just given the name and then we do actually have to figure out what we have. So this first step is really just figuring out what do we have? What are we working with? Once we know the four individual ions, because it will always be four individual ions, we have two cations and two anions. We move on to step 2, which is to determine the formulas of the possible products. We're going to do this by exchanging the ions. We're going to take the positive ion from one reactant and match it up with the negative ion from the other one. So we'll have two new compounds, essentially. We started with two compounds, each in their own individual solutions. When we mix them together, the only possible products we can make are these two products. We can never have more than that. We're never going to have 3 or 4 or 6 different possible products. It's always going to be 2. Now, if we were doing more complicated chemistry and we didn't have just one in each solution, well then, yeah, it could be possible to have more than 2. For our purposes, we are only ever going to have 2. So, once we swap the ions, take the positive from one, negative from the other, or a cation from one and anion from the other, we're then going to balance their charges to get the correct formula for each of those molecules. So if, for example, we swapped some ions and we ended up with barium and chlorine together as one of our possible products, we wouldn't leave it like this. Because if you remember, barium has a +2 charge and chlorine has a -1 charge. Again, that's based on where they're located on the periodic table. And so they don't balance out. And so we would actually need 2 of those, of the chlorines. And so that would give us our balanced charge. So once we have our balanced charges for the molecules, we're then going to determine the solubility of each of those molecules. So again, we'll have 2 molecules. We're going to look at our handy table, and we're going to figure out, is either of these molecules insoluble? If it is insoluble, then we would indicate that with a subscript of an S in parentheses. So if we check what I just wrote down there, actually let's pretend that I said it was lead. I know I said barium, but let's say it's not barium chloride, it was lead chloride, lead 2 chloride. This would be insoluble. And so to indicate that we know it's insoluble, we would write a little subscript, and sorry, I kind of ran out of space there, but a subscript S in parentheses. That S stands for solid. We are saying this is in the solid phase. And that is the only way that I know that you know that it is a solid. Which is to say, if you don't include the phases, I have no idea if you did the problem right, which means I'm just going to count it wrong. You must indicate the phases on everything in these chemical reactions. And for these particular chemical reactions, there will only be 2 possibilities. It will either be a solid, like the lead chloride here, or I guess I could have not scratched that out, or if it's something like this, it would be what we call an aqueous phase. So that would be AQ. Aqueous meaning that it is dissolved in water. Some people pronounce it aqueous, but I believe aqueous is the correct pronunciation. Alright, so then if we get to step 3 and we figure out that neither of the molecules is insoluble, then we just write no reaction. So we don't actually put anything after the arrow other than the words no reaction. Oh, I almost forgot about this. We kind of did this earlier, but I I forgot we had a couple extra steps there. So if there are any possible products that are insoluble, write their formulas as the products of the reaction using S to signify solid and AQ for aqueous. And then the last step here is if it is not balanced, go ahead and balance it. I would say it's maybe 50-50. About half the time it actually does balance itself. But and usually if it's not balanced, it's pretty easy to balance. These are not usually anyway. I don't want to say always, because there's exceptions to everything in science, but most of the time these are very, very easy to balance. Alright, so then again, just to give the same example that we saw earlier, potassium iodide and lead nitrate were the two things that we mixed together. And so to swap their ions, we took the cation, which was potassium, from the potassium iodide, attached it to the nitrate from the other molecule, took the lead, attached it to the iodide, and that gave us our two possible products, and that is what we checked against the table. And if you go and check, what you'll find is that the lead iodide is insoluble, which means that it is a solid, and the potassium nitrate is aqueous. Alright, let's do a quick example here. Let's write an equation for the precipitation reaction that occurs, if any, when solutions of potassium carbonate, which is this, and nickel 2 chloride, which is that, are mixed. Now, if I wrote these out and you're like, hold on a second, where the heck did those come from? How did you know that's potassium carbonate and that's nickel 2 chloride? It's all in the name. If you remember back to our nomenclature from chapter 2, I believe it was. If you remember carbonate, if you go back and look at that list of polyatomic ions, carbonate was CO3 2 minus, and potassium has a +1 charge, so I was going to need two of those to balance out the charge, and so therefore K2CO3. Same type of thing with the nickel chloride. Nickel 2 tells me that the nickel has a +2 charge. Chloride is -1 based on its location in the periodic table. And so I needed two chlorides to balance out the nickel. Alright, so if these are my two molecules that I'm starting with, I'm going to swap the ions, which really what this comes down to is as long as you write the name of the formula of the molecule correctly, you're going to take the first ion from the first one and pair it with the second ion from the second one, and then pair up the other two. Because the cation is always written first if the molecule is written properly. So just take the first one from here, match it up with the second one from here, and then just vice versa here. So second from the first, first for the second. And so that gives us a possible two molecules of KCl and NiCO3, nickel 2 carbonate. Now those are actually the correct formulas for those, because remember the potassium is +1, chlorine is -1, so you just need one of each to get a balanced molecule. Nickel is +2, carbonate is -2, so you just need one of each of those as well. So those are actually the balanced formula. So if I check the table, what I'm going to find, I'll go ahead and show you, is that chloride is generally soluble, and potassium is always soluble. So potassium chloride is definitely going to be in aqueous phase. Nickel and carbonate, on the other hand, we don't have a rule for nickel, but we do know that carbonate is generally insoluble, and nickel is not an exception to that. So, this is going to be in aqueous phase, and this is going to be in solid. And so, to write the full chemical equation, we're going to go ahead and write out what we started with. K2CO3 everything except for the product that is insoluble is going to be in aqueous phase. Just by definition, because we said that we started with solutions of these two, so they had to have been dissolved in water. And that is going to react and make KCl in aqueous phase and NiCO3 in solid phase. All right, so then we have one last thing we need to do. What is that? If you said balance, you are correct. We need to balance it. Thankfully, this is going to be super easy to balance. All I need is that. And voila, it is balanced. 2 potassiums, 1 carbonate, 1 nickel, 2 chlorines. And that's it. So there's quite a few steps in there, but none of the steps are super intricate or anything like that. It is just making sure that you're going through all the steps. You should end up with the correct answer. Okay, so let's do at least one more here. Go ahead and pause the video and give this one a try and see what you come up with here. So pause the video now. Alright, hope you gave that one a shot. What you would have found, what you should have found, is that we started with sodium nitrate, and it's reacting with lithium sulfate. We needed 2 lithiums, because the sulfate is -2 and each of the lithiums are only +1. And if you combine these together, there is no possible combination that gives you an insoluble compound, because you would match the sodium and the sulfate, both of which are generally soluble, sodium with no exceptions, and you would get lithium and nitrate, both of which are always soluble with no exceptions. And so this would give us no reaction. Alright, that's the end of these examples, but I think I actually want to do one more quick one. I'm just going to make one up here. Let's say that we still have the lithium sulfate. So that is still one of our things that we're mixing together. But now instead of sodium nitrate, let's do lead nitrate. That is something that is soluble. So we have lead 2 nitrate with lithium sulfate. So go ahead and take a look at this one. Pause the video and see what you can work out for this possible reaction. Alright, I hope you gave that one a shot. It's kind of similar to the last one because one of the molecules is exactly the same, and actually 3 of the ions are exactly the same. The only one that's different is that lead. But as I hope you figured out, that makes all the difference. So the 2 possible things we could make would be lithium nitrate, and actually I don't need a parentheses for that, because we only need 1 nitrate there. Lithium is +1, nitrate is -1, so we just need 1 of each. And the other possible thing we could make is lead 2 sulfate. And if we go back to our table here, let's see, it was lithium. Now I've forgotten what the other one. I know it's completely soluble. Lithium nitrate, that's what it was. Yeah, so lithium nitrate, most definitely soluble. Both of those are completely soluble. The lead sulfate, on the other hand, the sulfate is generally soluble, but lead is an exception. And so, this would be a solid, this would be aqueous, and so for our products here, we would have LiNO3 in aqueous phase plus lead sulfate. I ran out of space there, which is a solid. That really should be up right there, but there's not any space for me to write there. Only lets me write that far. Alright, so then the last thing here, boop, there we go. Like I said, if the equations aren't already balanced, almost always, they're very, very easy to balance. It's a pretty easy thing to balance those. Alright, I think we'll call it there for now. In the next video, we're going to get into acid-base reactions, which are kind of similar to the reactions we just saw, but they're also they're very different in that we're not going to make solids with these, but we are going to still have ions reacting together, and that's how they are similar. So we'll see you in the next one.